So what are orbital diagrams? Because they have some very useful applications if we can draw them for atoms. Well, first of all, what are they not? Well, they're not attempts to artistically and pictorially draw beautiful spheres for S-type orbitals and bilobed teardrops for the P-shaped orbitals, or the odd tetralobed or bilobed and donut-shaped d orbitals, or those god-awful F-shaped orbitals. Instead, an orbital diagram either uses a little line to represent each orbital, or in most cases, parentheses to represent each orbital. Now, how do we use these diagrams? How do we draw them? Well, I'll start off simply. Let's pick an atom such as sulfur, which has 16 electrons. Now, I want to start by actually writing sulfur's electron configuration because I'm going to work from that configuration to draw the orbital diagram. And of course, that means we're looking at a 1s2 and a 2s2 and 2p6 and 3s2 and 3p, 1, 2, 3, 4. So, these are the electrons I'm interested in placing into my orbital diagram. Now, to draw the diagram itself, I like to start by actually drawing all the orbitals for each of these 5 sublevels that I'm interested in. Now, since an s sublevel has only a single orbital, I'll draw a single pair of parentheses and label it 1s. A 2s, just like a 1s orbital, has only a single orbital, the sublevel that is, and so I draw a pair of parentheses and label it 2s. However, when I get to a p sublevel, like the 2p, there are 3 available orbitals for the electron. So I draw 3 pairs of parentheses and I label them all 2p. A 3s sublevel, like any s sublevel, has only a single orbital available. And a p level, once again, has 3 available spaces for electrons. Now, once I have all the sublevel orbitals labeled for my orbital diagram, I begin to fill them with electrons. And typically speaking, the electrons are represented by little arrows. So we're going to be putting little arrows inside these orbitals. And the arrows will point one of 2 directions, either point up or point down. And it's important that you consider the direction of the arrow because these represent the electron spins. And if we're going to place 2 electrons in the same orbital, we already know they can only coexist if they have opposite spins, because the magnetic fields that they each generate will be opposite, and those magnetic attractions will help overcome the negative repulsion between electrons. Literally, if I wanted to visualize it, negative will repel negative. But of course, if one of them is spinning clockwise and the other spinning counterclockwise, we would get different magnetic polarities. So south to north, north to south. And yes, south on this electron would attract north on this one, and vice versa for north and south. And we would get a minor attraction that helps to overcome the repulsion. It doesn't completely overcome it. Electrons would prefer to exist in their own space rather than share a space, but nevertheless, if it means getting closer to the nucleus, having lower potential energy by sharing a space, they will do so grudgingly if they have opposite spins. So for my 1s electrons, of which I have 2, I should draw 1 arrow pointing up and 1 pointing down to show that orbital is full. Same thing with the 2s, 1 up, 1 down. Same with the 2p. All 6 electrons will fill the 3 orbitals. And same is true with the 3s. Now, when I get to the 3p, which is a fractionally filled orbital, I take my time. And that's because of what's called Hund's rule. And Hund's rule states very simply that electrons will half-fill every orbital in a given sublevel before they will pair up and fill an orbital in the sublevel. And the translation of that is, yes, electrons just don't like each other much. They prefer to have their own rooms. So if I have to distribute 4 electrons over these 3 orbitals, I would put the first 3 in separate orbitals. Now you'll notice I have not done so randomly. I have put all 3 in these 3 orbitals, all with the same spin, and that is critical. Electrons that are not yet paired must all have parallel spins. So you do have artistic freedom. You can draw all of these pointing up or all of these pointing down, but the first 3 should all be pointing the same way. They should all have the same spin. And then, of course, we have a 4th electron. And all 3 of the orbitals are equivalent in energy, have identical energy. So which of these 3 spaces the electron chooses to occupy is a matter of choice. You can place it literally in any of them. Of course, most people choose to select the first one, and of course when you do so, you must have it anti-parallel, pointing in the other direction. It must have the opposite spin. And so this would represent the orbital diagram for the sulfur atom. Now, an offshoot of this orbital diagram is something very important. Clearly, in this atom, this pair, this pair, this pair, pair, all the paired electrons generate opposite magnetic fields, north, south, south, north, north, south, south, north. And because they get paired up, those fields cancel one another. So the atom as a whole would have no net magnetic polarity to it. However, whenever an atom, such as sulfur, has unpaired electrons, those unpaired electrons, however many there are, just 1, maybe in this case 2, 3, 4, up to gadolinium, which has a whopping 8 unpaired electrons, but any unpaired electrons at all give you a net magnetic polarity to the atom. Literally, both of these are spinning in the same direction. They have the same magnetic polarities, and this one would not cancel that one out. It would reinforce it, as a matter of fact. It would make it more north and south oriented in its magnetic polarity. And so, such atoms that have unpaired electrons and hence magnetic polarities are referred to as paramagnetic atoms. And they have the characteristic behavior of, once introduced to a magnetic field, they will align themselves opposite to that magnetic field. Long, short way of saying that is they're attracted to magnetic fields and will orient themselves so that their north coincides with the south and their south coincides with the north. They have magnetic behavior. So we can learn 2 things: how to write an orbital diagram, and then how we can use it to determine if the atom is paramagnetic. Let's do another example. Now that we have a clean slate, let's look at an atom such as magnesium, a metal. And of course I don't do anything until I have an electron configuration in front of me. So with 12 electrons, we'd have 1s2. Electrons 3 and 4 would go into the 2s sublevel. Electrons 5 through 10 would go into the p sublevel. And then the last 2, 11 and 12, would occupy the 3s sublevel. So in this diagram, we would have an s sublevel orbital, a 2s sublevel orbital, 3 2p sublevel orbitals, and 1 3s sublevel orbital. And of course, with 2 electrons, the first orbital would be complete. Second one, 2 anti-parallel electrons. Of course, 6 would fill all 3 of our 2p orbitals, and these 2 would fill the 3s as well. So an atom such as magnesium literally has no unpaired electrons. Every single orbital is occupied by a pair of electrons. And since each pair's north-south magnetic polarity would cancel that of its neighbor. The atom as a whole has no magnetic properties whatsoever, and therefore magnesium would be an example of a diamagnetic atom, namely an atom that has no magnetic polarity and would not interact at all with a magnet. Now, let's continue with another example. We've all experienced play with kitchen magnets, so we know kitchen magnets are attracted to certain substances, one of them which is, in many cases, a refrigerator. And of course, the major component that goes into building the refrigerator is iron. So maybe we should take a look at iron's electron configuration and orbital diagram. But we're going to shorten it by asking for an orbital diagram for all the non-core electrons in iron, those electrons that aren't part of the core. So I'm going to write a core electron configuration, a core abbreviated configuration. And iron would have as its core the same configuration as the noble gas argon, atomic number 18. So I pick up the configuration from there with 19 and 20, which would be 4s electrons, and 1, 2, 3, 4, 5, 6 electrons in the 3D sublevel. So when I'm trying to draw an orbital diagram for non-core iron electrons, I really only have two sublevels to consider. And those would be a 4s sublevel and a 3D sublevel. And of course, in a D sublevel, there are 5 available orbitals. So placement of the first 2 electrons is simple. They fill the orbital. But with 6 electrons and 5 spaces, Hund's rule tells me that the first 5 will occupy different orbitals, but all have parallel spins. And the 6th one must occupy any one of these 5 orbitals and have an anti-parallel spin. So we'll just, for convenience, put it in the first one. So yes, this would be the orbital diagram for all the non-core electrons in iron. And the interesting thing is that I notice we have 4 unpaired electrons, making iron very paramagnetic. Sorry, I ran out of space. And therefore, it would interact with a magnetic field. And yes, that's why our kitchen magnets would stick to our refrigerator. However, don't go making your refrigerator out of zinc, because if we chose zinc as the metal to make our refrigerator from, zinc would have as its core abbreviation argon and 4s2 and 3d10, which means that in its orbital diagram, all of the non-core electrons would be paired. And of course, all of the 18 electrons in the core are also paired. Those sublevels are all full. So it would mean that zinc would be diamagnetic, and therefore your kitchen magnets would not stick to a zinc refrigerator. I like my students to try and remember which is which, and a cute thing I often tell them is, if you don't want magnetic properties, just say diamagnetic, die! And then you'll remember that that's a reference to the atom that has all paired electrons.